We seem to have some difficulty with audio, and so I'm just speaking to test whether the audio is working. If not, I hope we can find some way around it.
Hello, am I heard?
Yes, so
Okay.
Ching Huang, so you're okay?
Yes, yeah, I'm okay.
Okay.
So, do I start
Yeah,
now?
you can start. Yeah. So we're very pleased to have
Okay.
Ching Huang speaking on asymptotic dimension, and
Mhm.
so just go ahead. Yeah.
Okay, so maybe it's the last talk for this special session, and everyone is looking for the spring break, right? And so probably I'm going to talk about 20 minutes about some recent work about the dimension theory for a special case of the quantization story. And to start, okay, the background. So what's a classical quantization problem is to discretize a probability measure by by finite combination of the discrete Dirac measure, and so which means we need to minimize the following function. So and we are minimizing the LP distance from a finite supported measure to a probability measure P. And there is a alternative definition using the Wasserstein's distance in terms of the optimal transport. And here, so the the minimizer of this problem is a set with cardinality less than n. So a finite set. And so in the classical setting, we can define the quantization error in this way. So uh, and for R is less than infinity and R is equal to infinity, the setting is a little bit different. And here is the classical LR distance, and for the infinity sense, it's also the covering radius of the support of a probability measure. Okay, so what's the constraint case? Uh, 2 years ago, Moreno and uh, uh, Mark Harpendi, they introduced another case which so what will happen if we constrain the minimizer of this problem to a closed set? And the things turns out to be a little bit different. And they studied several examples and they have some basic results about the behaviors of the minimizers in this case. And yes, and so here we can rewrite the errors in terms of the constraint setting. But okay, so let's go on another page. So if the R's momentum of the probability measure is less than infinity, then the limit of the the minimization problem as n goes to infinity exists. So we can so this term is well defined, and we can subtract this term, uh, which implies the implicit geometric obstruction between the constraint and the support of the probability measure. And so in the following of the presentation, I'm going to study the minimization error E tilde. Um, yes, and for the case R is equal to infinity, it's also well defined, but we need to using the Hausdorff distance. And so what's the next page? And the about the dimension theory. And so in the classical setting, we can define the quantization dimension of which can measure the asymptotic rate that how the quantizers can approximate the probability measure. And in the case R equal to infinity, it's how the covering radius can approximate the support of the probability measure. And so and so we I analogously define the quantization dimension of the constraint quantization case here. So dimension tilde of RQ. So the upper bar and the lower bar in this case means the upper dimension and the lower dimension. So what does the classical dimension theory tells us that if the if the geometry of a set is good enough, then the quantization dimension of the set, so of the probability measure supported on this set collapses with the other standard dimension. For example, the Hausdorff dimension, Minkowski dimension, and the Renyi dimension in some case. And the quantization error has an asymptotic rate n of 1 over negative 1 over d. So here are some wrap up of the classical result on the dimension theory. And the most fundamental work in the unconstrained case was summarized in the work by Graf and Laschke 20 years ago. And there are some beautiful comparison formula between the quantization dimension and other classical dimensions. And there are some extension work maybe 10 years ago by Klockner and Dai and Liu about, yes, and specifically if P here is ADR and compactly supported on some Riemannian manifold, then we say that the quantization dimension coincide with Alphonse dimension. And so here, for the specific problem of the constraint case, we can expect that the challenges of the constraint case is much different than the unconstrained case. And yes, the main challenges come from the positioning of S and K, of the constraint and the support of K, and the geometry of S and K themselves. And by the work by in the work by the Pandy and Marino, they discussed a lot of cases where where the geometry of the constraint they can impact the degeneracy of the minimizer and a lot of and uh, and there are a lot of other examples. So to study how the positioning of S and K and the geometry can impact the quantization dimensions, here we introduced the notion of the metric projection. So this is an old technical tool, maybe in convex geometry, and it's defined by, so the metric projection send one point in the probability measure to the set of elements in the constraint which has the minimal distance from that point X to the to the to the set S. Yes. And why the and and here the metric projection is a multi-valued function, but it has good property and we can, so there exists a single valued metric, so measurable function t from k to s, such that we can treat the metric projection as a single valued function. And if the constraint has good properties, for example, the constraint is convex, then the metric projection is automatically single value. And yes, and so here comes to the main result of the upper asymptotics and the lower asymptotics in this case. So here the first result, if we assume the the condition U here, which says there exists a sequence of the quantizers which can approximate the projection of K on S in Hausdorff distance, then we can have an upper bound of the Hausdorff dimension with respect to the quantization dimension defined above. And in one word, the upper asymptotics are controlled by the geometry of pi sk, and also in some sense the the lower density of the push forward measure T star P. So here and there is a and there are also some result about, so we can have the upper bound in terms of the Minkowski dimension. And here, so for the proof here, so the major technique in this case we use is we use the we use the triangle inequality induced by the metric projection, so we can pull back the the quantization problem constraint on another set S to another problem. So we can instead study the En infinity of pi sk, but the constraint is a compact set itself. And so the step two is we can use a stopping time argument in this case to show that if a set is compact and the constraint is the compact set itself, then the the quantization dimension when n is equal to when r is equal to infinity is bounded by a constant only dependent to the dimension d. And here recall that the um, recall that the when r is equal to infinity, the quantization error is called uh, this allows us to argue by contradiction and show that the 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 cardinality of the quantizers alpha n is larger than n. And then we can use the property that E is measurable, and we push forward the uh, and we and we study the constraint quantization problem on another measure T star P, and we can and the proof is very similar to the classical setting. And the construction for the lower asymptotics is more interesting than the uppercase, I should say, because here we use some technique which is in spirit very spiritually very similar to the good lambda technique here. And so here we define two auxiliary functions, so HAI and GAI. So we can say that so the constraint quantization error in this case is the integration over HAI. And the function GAI can be understood as another so is very similar to the quantization error um, of of the case when the constraint is the probability support itself. And here we define a good set A lambda T here. So in the good set, the HAIX, this function cannot be too small, which prohibits the case when HAI has the lower bound as 0. And so we can have a local version of the good lambda type estimate here, and we use the estimate GL and GL prime to plug in the terms of the quantization error and using some standard layer cake decomposition here, and we can have the quantization error has a lower bound of this the summation of the integral of GAI here. And on the other hand, we can use Frostman's lemma and the Holder's inequality to find the lower bound of the integral of GAI here. So we can see that the term, the quantization error term n power 1 negative 1 over d naturally emerges here. And so so we can define a new quantity eta n lambda t here. So if this quantity has a lower bound, if this quantity has a lower bound on n, fixing some lambda and t, then we can say that the lower quantization error has, uh, uh, we can find a uniform lower bound in this case. And there is another condition satisfying this. So L is another condition for the lower bound, which can make the quantity here has a uniform lower bound. So the assumption here can be understood as some density argument. So for each point of the quantizer, which is in pi sk, then we can find we can make a small perturbation to find another point on which is in the constraint rather than the projection of k on S. So to make the distance between A and A delta is not small enough. And in this case, we can say that the lower quantization dimension has a lower bound as the Hausdorff measure here. Yes, and so if we combine the upper and the lower estimate here and assume a stronger upper and assume a stronger condition U prime other than U, then we can have a straight equality here. Okay, and I have a following example here. In this case, so this is an interesting example so we can calculate that the quantizers in this case, they are not in the projection, but they are strictly lies in the set S rather than the metric projection. But we can also see that the quantizers, the Hausdorff distance between the quantizers and the metric projection K, they has the asymptotically has the Hausdorff distance as 0. So we can say that they have an upper and lower quantization dimension here. They both coincide as 1. And here, and I'm going to make a small remark about, so what are some interesting things in my recent work? So maybe, so the first thing is can we construct some explicit examples which has some dimension gaps using the quantity here eta n? And secondly, can we find a strict equality in terms of the Minkowski dimension? And what are the extra conditions we need in this case. And third is because in the proof we use the spirit of the ADR, and can we use, so can we impose some more natural conditions like UR and NTA, which can control the geometry of PySK? And, and can we extend this proof for some more meaningful settings in harmonic analysis and PDE in this case? Okay, so this is the end of my presentation. Yes.
Thank you very much. So let's thank the speaker, Tin Chang. And if there are questions, please ask away. The organizer emailed me and said that his microphone isn't working, so he asked me to close this morning sessions. And I thank all the speakers in the session here, and I really appreciate the great talks. And in addition to that, I want to remind you that there's a program for all the sessions, and there's a link you can click, and it's been communicated by the email, or you can Google it so that you can attend the later sessions as well. But this one here is the last talk in the morning sessions. So thank you very much, everyone, and see you later. Yes.